I will jump directly to the point and to the topic today of Farapulse pulse field ablation system. You will hear me speaking about PFA to make it faster and easier. So first, we will cover the therapy, its mechanism of action that will essentially explain the two specificities, very important specificities of electroporation compared to the other ablation therapies, which are first the tissue selectivity that this therapy enables, and second, the potential safety benefit that you get, as this therapy is essentially a non-thermal energy modality. So the mechanism of action is we are really looking to obtain an irreversible electroporation. That's totally essential. How can we do that? A precise electrical field is applied to the tissue. It will disorganize very rapidly the membrane of the cells, and ultimately leads to the formation of pores into this membrane, nanoscale pores. Then the content of these cells will exit through these pores, leading to the cell death, essentially by an apoptosis mechanism. What is here really important to understand is that there is an intermediate stage where these pores that has been created into the membranes can refill, and the cells can come back in its initial state, and this is what we call reversible electroporation, and that's what we want to avoid absolutely. So as Pierre was mentioning this morning, this disorganization of the membrane cell is really what we see as a cardiac stunning, so an immediate reaction on the screen, on the PV potentials that are blocked. But this lesion has to mature over time, as we want to create, of course, durable lesion. So here on the right side, you can see that there's really a continuum depending on the electrical field that is applied on the y-axis and the pulse duration that is also applied here on the x-axis, between like no effect at all in white here, going through a domain of reversible electroporation, then reaching this field of irreversible electroporation for a certain window of pulse duration and of electrical field strength, and finally arriving for very high electrical field and long pulse duration in a thermal zone that we absolutely want to avoid. So how can PFA specifically target cardiomyocytes? I was really talking to you about the tissue selectivity, and this is totally unique to PFA. As a matter of fact, any cardiac cell can be ablated by electroporation. It's just a matter of the sensitivity of the cells to the electrical field. And we are here very lucky because the myocardium has a threshold that is really low compared to the adjacent structures like red blood cells, vascular smooth muscle, or even endothelium, so 4 times lower than these structures, and even 9 times lower than the nerves, which means that by applying a certain level of voltage, we will only ablate myocardium, leaving all the other structures unaltered. Here on the left, you've got a transmural ablation of the tissue, keeping really undamaged the endothelial layer, the nerves, and also the blood vessels that are running through this piece of endocardium. So really, thermal energy can differentiate. PFA is tissue selective. As you know, really with a thermal ablation that we've been using for like decades now, RF or cryo, we are ablating through thermal lesions with radiofrequency, and we can of course get the linked complication, the potential complications that you all know: PV stenosis, atrial fistula, that is the worst one for essentially for RF, and on the cryo side, the phrenic nerve palsy. On the electroporation side, of course, this structure will be surrounded by the electrical field, as this field doesn't stop, but they will be unaltered by the field. Regarding the fundamentals of the delivery, there are really different modalities of delivery for PFA and a lot of different parameters where we can play with. First, the mode of delivery. There are two different modes. The first one is the monopolar one, with the electrical field created between an active electrode on one side and a dispersive patch. I mean, it looks like a little like the RF energy. This delivery mode has multiple drawbacks, particularly the ability to capture a skeletal musculature, meaning that it required absolutely general anesthesia on one side, and paralytics may be also necessary. The other way to deliver the energy is the bipolar way, which means in between the electrodes. But for this kind of delivery, really the conformation, the design of the catheter is really critical to avoid, for example, arcing between the splines, and also to achieve a depth of the lesion that is enough with this delivery. Then we will hear a lot speaking about the waveform that we are using. This waveform is typically the type of pulses that we are applying on the tissue. Here, a description of the multiple parameters that you can play with, the voltage, of course. Either it can be monophasic, which means, for example, here only positive voltage, or biphasic, positive and negative voltage. The spacing of the pulses plays a role. The interval also between the spacing, between the pulses, and even the shape of the pulses can play an important role. So there's clearly, and as we saw that with the irreversible electroporation, you cannot determine how your lesion will evolve. And that's really critical to understand. Making an ablation with electroporation is like very easy to do. You get an acute block of the potentials, but getting a mature lesion in the time is much more difficult. So what we are doing with Farapulse, we've got a system that is bipolar. The energy is delivered in between the electrodes and in a biphasic mode. So as I told you again, really its system may achieve an acute isolation via this cardiac stunning, but the long-term durability is key. And yeah, with this type of energy, Farapulse was really the very first one to prove the long-term maintenance of the lesion at 3 months by an invasive remapping of the patient. So now the system, you will see it's a very simple system. We are using a deflectable sheath, large one. It's a 13 French internal diameter. It has one very nice feature, I must say, that is a translucid sheath that really allows to potentially see air bubbles into this system, and it really adds to the safety of the complete system. The FARAWAVE catheter, we used to say that it's our flow shape, so it's a pentaspline catheter mounted over the wire. You can record potential in the veins with the third electrode that is at the equatorial positioning of the catheter. It comes in two different diameters, 31 and 35 millimeter, and can be deployed in two essential shapes that are the basket one and the flower one. This is a non-deflectable catheter, but irrigated. So this knob here is there to modify the shape of the catheter. And finally, the Farastar ablation generator will be able to deliver this optimized waveform. Very, very few parameters that you can modify. It's only the voltage that can be adjusted from 1.9 to 2 kilovolts. And we usually use 2 kilovolts now for all the procedures. And that delivers, again, I repeat, bipolar and biphasic waveform. Here, these animations that probably you've seen already during the pause, but I think it's quite important to again, have a look at that. You will see here a simulation of the electrical field, but which is very realistic in terms of simulation. Wiring of the left superior here, positioning in a flower shape. Here, really, the electrical field that is created with the catheter, and you will see that it will cover the esophagus here on the posterior wall, but without affecting the cells. We can see also that we are always like looking for contact, not pressure, but contact, looking at the splines going backwards when we are looking at the catheter on the X-ray. The second positioning will be in the right superior. So then sheath is retracted, catheter also undeployed, and then the right superior is now targeted. In the right superior, it's very often that we get a capture of the phrenic nerve, which means stimulation for the patient. Here also you can see that the size and the shape of the electrical field is slightly different. Same thing here, the nerves is included into the electrical field, but not affected by this modality of ablation. So that's essentially what I wanted to present to you. Pierre was referring to what's coming next, but this topic will be covered by Tobias, who is in my R&D team tomorrow. So we keep the best for tomorrow.